I'm going to start, I guess, so people can have time to join us. Right. So I'm going to talk about the rotation mechanism for fair task. So what is it? So some people saw that when executing some workload on HMP in particular, the workload was dividing the actual work in a static way and in different threads. So you create n number of threads, as many threads are as the number of CPUs, and then the work is so each thread has to execute the same amount of work. It's a bit problematic on HMP because some CPUs are more powerful than others, and it means that, for instance, here, so I have a pointer, the thread which was lucky enough to start on the big CPU will finish earlier. The thread which started on the little CPU was a bit unlucky. It's going to be migrated up to the big CPU. And here, we have an idle CPU during quite a long amount of time. And the workload is going to finish only when the last thread returns. So it started like that, and it became a more generic question, which is how can we track forward progress of different threads of different tasks between CPUs? So I'm going to start to talk about the load balance, what I'm interested in this specific case, how to define a forward progress metric, show some task rotation, because that's what it's all about in this example, and then a small conclusion. So I'm going to make simplification at first. So in scheduler, we can define a nice priority, which is supposed to, for a task, give more importance to some task rather than, and some tasks are tagged as more important than other, and they should receive more running time compared to other tasks. It's, in my case, I'm only interested in long-running tasks and in an overloaded system, as I showed in the previous slide. So I'm making an approximation, simplification, which is that the nice priority is somehow related to the load. So the higher the load, the more important the task is, the higher the load, and the more running time the task should receive.
Yeah, one question: when you say overloaded, it's more tasks than CPU, or it's one task per CPU?
So what I mean by overloaded is that there is no more idle time.
Okay, no, it's just because it's
right.
Overloaded is more than one task per CPU.
Yes, exactly. So the goal of the load balancer in this exact scenario, when you have, so in this case, you have more tasks than number of CPUs, is to try to balance the load between the different CPUs regarding to the relative capacity of each CPU. So in this case, we have a 3 tasks and a CPU with a capacity of 1024, 2 tasks on a CPU with a capacity of 256. The ratio of load divided by capacity is obviously higher on CPU1, it's 8 compared to 3. So the load balancer is going to migrate one task from CPU1 to CPU0 to balance the two.
Oh, sorry, just a quick clarification. And this was more of the previous slide, but the concept that we're prioritizing longer running tasks, I was wondering if you just unpack that intuition a little bit more, because it sounds like the opposite of what schedulers like LAVD are doing with this latency criticality heuristics, where you're assuming that short running tasks that wake up a lot and have a wake-or-wakey relationship with other tasks are more likely to be on the critical path for things like I/O. So you want to actually schedule them first over, quote, hogs that are using a lot of CPU time. So why the opposite?
So in my case, I'm only interested in CPU-bound thread tasks. So there's no such thing as low latency. You don't want a task to react really fast. It's only tasks that are going to run during maybe 200 or 300 milliseconds. So latent and starting to run 1 millisecond before, it's not super important in this case.
Got it. So we're thinking like maybe a batch
yeah, exactly.
processing context or something like that.
Yes, exactly.
Okay.
Okay, so the load balancer is going to balance the load between the different CPUs regarding their respective capacity. And this relies on the assumption that if we put the same load on each CPU, all the tasks are going to progress approximately at the same rate. This is, yeah, so this is a CPU view of what's happening, meaning that we don't actually see how each task is progressing individually. We just see everything from a CPU point of view, to try to balance the load. Individual task progress don't really matter or exist actually. There are some situations that cannot be balanced by the load balancer right now. So the first situation is what I showed in the first slide. So you have only one task on each CPU. Yeah, in the first slide. So you have only one task on each CPU on HMP. The task which runs on the little CPU receives a lower throughput. It's unfair, but right now we don't balance this kind of scenario for multiple reasons. One reason is that if a CPU is fully utilized and there is already one task running on the CPU, we consider that it's balanced. Also, we don't have any metric to actually compare how each task is progressing between T0 and T1. And yeah, also the load balancer is only pulling tasks, so we cannot swap tasks right now. Second scenario is on SMP, so each CPU has the same CPU capacity. If we have 3 tasks on 2 CPUs, the load balancer is going to be able to migrate one of the tasks from CPU 0 to CPU 1, but it's going to be a more or less random choice. So you pick one task to balance it, and then after some time, CPU 0 is going to pull back one of the tasks, but because it's a random choice, T0 might always be picked, which means that T0 is always going to share the CPU with another task, and T1 and T2 are going to progress a bit faster than T0. So it's also a bit unfair, but we are not handling this case right now. What we should target, or ideally what we should aim for in this kind of situation, is to have each task receiving receiving the average capacity of the platform, which means that on the first case, so the average capacity of the platform is 1024 plus 256 divided by 2 on the example B. So it's, you have 3 tasks, 2 CPUs. On average, you should receive 682 capacity. So it's yeah. And exactly how it should look like is, instead of having one task running for some time on the big CPU and then migrate task 1, you should swap tasks from time to time, try to even the progress of each task. So to do that, right now it's not really possible because we don't really track any forward progress metric at platform level per task. So we have a V runtime which tracks the forward progress of each task on one CPU. We have the PELT value, which is a way to track so it allows to estimate the size of the task, but we don't actually track what the task is receiving, the throughput. The ideal implementation would be to have a global V runtime, but it's not possible to have that. It's don't scale.
Not only does it not scale, you get into trouble if you have overlapping or even non-overlapping affinity masks.
Yeah.
V runtime gets to be a massive headache and all kinds of corner cases that are interesting.
Yeah, but for many reasons, it's not possible to do that. So the solution that was found so far is to measure the received throughput of each task and consider that this is the forward progress that the task is receiving. So it's an approximation, it's not actually correct. And it's more or less equivalent to revive for people who were there many years ago, I guess. What was called the contribution scale PELT, which measure the throughput that each task is receiving instead of estimating the size of each task. So, for instance, we have in blue a task running on a big CPU, purple a task running on a small CPU. Right now we have PELTs, which is an invariant signal, which means, as I said, we are trying to estimate the size of a task, which means that for the two tasks, at some point, we should consider that the two tasks are really big and should reach the maximal value, which is 1024. So the two plane line, it's the PELT invariant signal. And the contribution scale PELT utilization, which is equivalent to a throughput measurement, is the dotted line, which is what the task, the purple task, is receiving on the CPU1. So CPU1 has a capacity of 256. The throughput is 256. So it works. So if you start to do task rotation based on this signal, so you can achieve something. So it's same example, one big, one little CPU, you rotate task on average. So this graph is the average throughput that each task is receiving. When the task is running on a big CPU, the throughput goes up. When the task is running on a little CPU, the throughput goes down. And we try to actually balance not the throughput that we receive, but the ratio of the load divided by the throughput. So to next slide. So what I did in this prototype is to also take into account the nice priority value, which means that if someone decides that a task is more important than another, it should also be taken into account inside the rotation. So we don't try to balance the throughput of each task, but the ratio of the load divided by the throughput, which makes more sense in this case. About how often we should rotate tasks, it's so we are using the mechanism is based on PELT, which has a certain half-life value, which means that the signal is more or less valid during a certain windows of time. If you look at the PELT values that are at 1 second, you don't really have any meaning anymore. So we should rotate reasonably quickly. So let's say between 50 and 100 miles per second, it's possible to configure that. And, yeah. So the mechanism is also trying to tag and detect long-running tasks. So if the task has been running for some amount of time, you tag the task as a long-running, and you consider this task for rotations. It's possible to do some other things as well once you have tagged the task as a long-running. And the rotation is, in the previous example, we check for rotation on a tick base. So every time there is a tick, we check that if there is a long-running task on a smaller CPU, should we swap or not? If this is the case, we log the to-run queue, we migrate the task, and we continue. So it's pretty similar to what Vincent did with the push-pull mechanism to check things on a tick base. But it's some limitations, some difficulties that this prototype has is mainly that. Yeah. Right now, it was I would say yes. because it's only targeting HMP, so it's not really, you don't have many LLC.
So how do you incorporate the cost of this task? Might have been task or cash out.
So right now, so it's not incorporated because so in the prototype, the only consideration is how to be fair and not how to, because there is also, I mean, it's arguable, but there is more gain to be fair regarding the two tasks rather than being cash out. I mean, you could compare this. It was not compared in this example, but it's not considered. Yeah, so some issues with the prototype. So an issue is that it's not so easy to find some workloads that are doing static partitioning of work most of the time. So
isn't this pretty much all scientific workloads ever?
So there are some workloads, but effectively it's the investigation stopped more or less is that we were not was not able to find good example where it's actually useful.
So all the PDE solvers, they typically run chunks and then have a barrier for completion, and then issue another bunch of chunks and then have another barrier for completion. So they should hit this issue fairly often. I mean, you're always waiting for the last man to finish.
Yes.
And this is a very common pattern in the scientific world, as far as I know.
How long are they? How long does it take? How big are the type? Because it only really makes sense if it's way longer than like 50 minutes.
Yeah, I'm not sure.
And also, are they using SMP?
Yeah.
HMP?
I doubt it.
And in this case, on this scale, I mean, they split that, so they can probably split according to.
Yeah, so and typically the scientific guys, they spawn as many threads as they have CPUs, and it's just a few threads get delayed by system services and other crap, like somebody SSH into the machine and that task gets stalled, and then the whole machine goes idle waiting for the time slice to recover. But yeah, I don't know. We need to find somebody that works in that space.
So the main example where it worked was for compression algorithm where, but again, you need to have, you can choose the size of the chunk that you want to compress. And if you choose correctly the size, you need to have big chunks. If you choose it correctly, it's going to be beneficial. Otherwise, there is most of the time what happens that you create as many threads as the number of CPUs, and other threads are pulling from time to time work from the pool of work. So if you do a rotation, it's useless because you have more work item than the number of CPUs. So you rotate things, but it doesn't improve things. Yeah, so first issue, which is the biggest one. Second issue with the implementation is that it's only solving the HMP issue, not the SMP. And so the last one, it was more or less solved by using the tick-based integration. One issue that I had was that the load balancer runs less and less if CPUs are busy. But in our case, we want to run the load balancer quite often if all the CPUs are busy. So it goes in different directions. So that's why I had to move to CPU.
It might be that video editing workloads and or image manipulation might also.
And so I try to find something in this area as well. And maybe there is something that I didn't find. So about the SMP issue, so still, ideally, what we would like to do in this case is do some load balancing, but not from a CPU point of view, but from a task point of view. So instead of having a ratio load per throughput, you have this. So you have this ratio, but per task. So here the ratio is 2 and 2 for the tasks that are co-scheduled on the CPU. The sum of the ratio on the CPU 0 is 4, so you do an addition. Sum of the ratio on the other CPU is 1. There is an imbalance. You want to solve this imbalance, you move one of the task. The sum of the ratio is now closer. The delta between the two ratio is less. But yeah, it's still imbalanced because CPU1 appears are more loaded as CPU0. So if we would like, if you wanted to go further, task 0 should try to steal some running time from task 2, which means too many modification. It goes a bit too far, I think. And also, one important issue that we assume that all the tasks are long running, which is not the case. So it's a bit like we are trying to solve an issue which is really a corner case in practice. And yeah, other issues were that you would need to rewrite everything from that perspective, but it's not what we should do, I guess. So ultimately, the conclusion that it's a bit hard to push for such mechanism and to rotate tasks and to have a forward progress metric. But still, in the meantime, and while doing the prototype, it appeared that we used the PEL signals, not using the invariant clock, and yeah, not so. It's a bit more specific, but I had to create wall clock based PEL signals, which is actually something which is more correct for load on runnable computation, because the load on the runnable signal are representing more a waiting time, and you should not delay the time of the waiting time. It's not representing anymore what it meant initially. So there were some workloads when one specific workload on one specific platform where there were some improvements by switching to wall clock based PEL signal. The second thing so I had to make some detection for long running task. It's also something which could be convenient for some cases. For instance, right now we only have PEL, which doesn't. We are for long running task, PEL values are a bit. PEL utilization values are a bit meaningless. So we are doing some arithmetic on values which are a bit meaningless after some time. For instance, here, if you have two long running tasks on one CPU, if one of the tasks goes away, you end up with one task with a utilization which is not the maximal utilization. You could have a frequency drop. It's a bit weird to have. So we still something to save might be that. And yeah, also last thing so right now we have the PEL utilization, which aims to estimate the size of a task. But if we are on an overloaded system, estimating the size of a task is not really useful anymore. What we should maybe use is this throughput signal, which shows more what each task is actually receiving. And yeah, so that was the three things that might be saved if someone is interested. Otherwise, rotating task, it might be over engineering, I guess. And yeah, if there are any questions or remarks.
So there are, like when you do the rotation, of course, there are caching implications, right? You may increase the amount of misses. Are you taking into account any sort of like migration cost or?
So not right now.
Okay.
The only aspect that was considered was how fair we can be regarding to running time, not regressions.
Yeah, because I'm asking because we tried to do a similar, actually the same thing, the same rotation on using SCADX on the DGX Spark, which has big and little, fast cores and slow cores, but so in that particular topology it's even more complicated because there are two L3 caches, each one with fast cores and slow cores.
Okay.
So if you rotate within the same L3 cache, it actually works really well. If you start rotating across the two different L3.
So the way to find a CPU to rotate is, so you just, actually, yes, the rotation happens inside the LLC. So you,
Okay.
I mean, it's just a CPU mask that you can choose to iterate over to look for
That's
a little CPU, but it could be at a platform level, to a smaller level. You can do what you.
Yeah, that makes sense. And the other thing, have you tried? So yeah, Peter was mentioning the video encoding. So in my test, when I tried this on the Spark, I found that like video encoding was actually progressing, but video decoding was improving for some reasons that I don't know. So maybe you wanna try that if you haven't.
I mean, so what I could see, for instance, so it's more for text compressing, but if you divide a file to compress into chunks, you might have, for instance, you have 2 CPUs, 3 chunks. The big CPU might have the time to do the 2 chunks before the small CPU finishes. And depending on the CPU capacity of each of the little CPU, rotating or not, it might be beneficial or not actually. So it's can be something.
Could you estimate the possible theoretical improvement of doing the rotation?
So it was actually a bit costly. It was a bit costly. I don't remember, but.
Because the last time I saw that doing the rotation, if you have 1 task per CPU with big and little, only big and little, I think that the best improvement is 13% from the last time I looked. And it's mainly when your little core is half of the big core, as soon as you.
Right. So I didn't, when I checked a bit, it's really, what you can gain is really dependent on the topology.
Yeah.
And it's not something that you can compute. It's really topology dependent, and I don't have a formula to compute the maximal benefit. If in the example that I showed, it was 8%. On a different topology, it might be more, it might be less. So, but it's not going to be more than maybe 30%, as you said. It's not going to be.
And if you have a large difference, then I think it's few percent at the end. If you have a really little CPU compared to the big, then the benefit.
Yeah, it's
less.
twice.
It's less.
Yeah. Yeah.
Yeah. Probably not a question, just something I want to share when we try to do this. Yeah, we have an engineer that tried to make this work. The most difficult thing is how to decide a task is a long running task. This turns out to be super difficult. And in the end, we often have this situation where we think it's a long running task, and then we start rotating, and then we decide, then we found, it's not a long running task. Then this is hurt performance by quite a lot. So in the end, we implement another mechanism on top of that. So when the big core now becomes idle, it then checks whether the little core is running a just rotated task, and then we try to pull it back. Because if the big core becomes idle, then it means that you think it's a long run task, but it's actually a short run task. So you have to mitigate for the mistake you just made. And then we have a mechanism on top of that. But even then, this mechanism still doesn't give you that much. So I just want to share like our experience that we try to make this work, and then we have many mechanisms on top of it. But then in the end, it's still like you probably cannot enable this in a generic way. You can only enable it probably in Geekbench. We found there is a performance improvement in Geekbench, but like we have to have a allow list of whether this can be enabled, but enable it in a generic way is super difficult.
Yeah. So right now it's only for just save the moment the task starts to run after a certain amount of time, which is arbitrary effectively, and it depends on the pelt half-life. So it's right now it's maybe between 50 and 60 milliseconds. To consider that the pelt values and the pelt utilization values is a bit meaningless. The task is just really big, and that effectively it's a static value. On in some workload it might work. On some other workload it might not work. But you cannot know whether the task is going to end before it ends. So, yeah, otherwise, thanks for me. Thanks everybody.
We are early, but okay, then.
Okay, so sorry, question. If you're, sorry, just one more. So my understanding is that this was modifications to Fair.c to implement this prototype rotating. And I was just curious, coming from the SCEDX side, if there were specialized workloads where you wanted the rotating dynamic. Seems like one way to do it would be to have a SCEDX scheduler that did it for you for your like scientific workload, your OpenMP, your MPI that has kind of gang scheduling with a global barrier. And what are we missing from SCEDX to have done this experiment in a SCEDX scheduler?
Which mechanism do you need in SCEDX to do that? Or?
Yeah, well, to do the experiment with the rotating prototype, what would it have taken to do it in a SCEDX scheduler as opposed to do it directly in the entry?
So I haven't looked much at SCEDX, but I think you still need to have some way to estimate how the progress of each task. But
yeah,
Ryan, I can pick it up in my talk if you're.
Okay, cool. Thanks.
Right.